Welcome again. In this presentation, we will present a solution to anti-windup through pole placement. We will explain how this 2-DOF pole placement controller works, and then we will demonstrate how it solves the problem that we presented in the previous video. We propose the configuration here as anti-windup control, where we have new variables like P, E and F. We have the familiar TC, SC. Of course, we do not have the RC here. It may be possible that we will introduce RC later. Maybe one of these parameters could be written in terms of RC. They may make up the standard 2-DOF control, but we have to verify that. And we could possibly design that using our pole placement strategy. Let us see what happens when the saturation block is not active. That is, the control law calculated by our controller is within limits. Then this gain block can be replaced by 1. This saturation block can be replaced by a gain of 1. So when within limits, we will find the expression for this closed loop, inner closed loop. So we can write the transfer function of the inner loop as T, which is equal to 1 over 1 minus E by F. The gain here is 1, and there is no negative feedback here, there is positive feedback, so we have minus sign here. When I simplify it, it becomes F over F minus E. Then I replace this inner block with this F over F minus E, and the F in the numerator will cancel the F in the denominator, and as a result I get this whole thing replaced by 1 over F minus E, and there is no change in any other block. Now can you see whether I can replace F minus E with something we have already seen? Now if we define F minus E equals PRC, of course this P is yet to be defined, but whatever that P is, if we choose 1 over F minus E to be PRC, then PRC will come in the denominator. You can see that we will get the standard 2-DOF control because this P will be cancelled. So the configuration that we had earlier reduces to the standard 2-DOF configuration when limits are not exceeded. What happens when the limits are exceeded? That is, this saturation block is no longer inactive, it is active, so the gain is not 1. That introduces some disturbance into the system, which is modeled by an auxiliary input called delta. So this is in some sense an equivalent representation with the saturation block replaced by an external signal delta. So what we will do is we will take this signal point from here to here. So I will bring it from here. When I do that, then I have to multiply this E by F with the reciprocal of this. So I have Z power K into A by B. What happened to this F? Why is it not here? That is because I shift this point also over here. So this F is already there, so I do not have to put this F. So this block and this block are identical. I have not changed anything else. Okay, let us further simplify this. Here is the block that we arrived at in the previous slide. Now let us get the transfer function between the signal delta and Y. In particular, we want to understand the effect of this delta on this Y. We want to minimize the effect of this delta on this Y. In order to do that, we identify the transfer function between these 2 points. So T delta Y is given here. It is very easy to explain this. the forward transfer function is given here, z minus k, z to the power minus k into b by a, that is the forward path. In the backward path, what you have is 1 plus, because of this minus sign here, and then you have to multiply the 3 gains. One gain is here, 1 over f comes here, another gain is the planned gain which is here, and the feedback path, what we will do is we will merge this inside this, and because of the minus sign you will have to put a minus sign here. You put a minus sign, you put it here, that comes here, PSC minus the gain that we have in this block, that comes here. So as a result, this is nothing but the transfer function between this delta and y. Let us simplify it. So once again, this is easy to explain. So this a is taken down, so I get this a. When I bring it down, that a cancels this a, and then what I do is I take this f to the numerator, I need to multiply this also by f, and then I take this z power minus k into b by a inside. So we will have z power minus k into b coming here, this a was already cancelled by this a, so we get this expression. Similarly, this z power minus k cancels this z power plus k, and we are left with EA. So when I simplify this, I get this expression. You have to verify this. So the denominator consists of a term that has a. We will group this 2 terms containing f and e. So we have f minus e into a plus this second term. Now recall that we defined f minus e as PRC. This is what we had written in blue earlier. I substitute that in the denominator. So the numerator remains the same, z minus k into bf. The second term remains the same, z power minus k into bpsc, and here f minus e becomes PRC. So I have PRC into a in the place of f minus e into a. So this is the transfer function between the new signal delta and the plant output y. Now we will see how this transfer function behaves. Let us choose f to be ARC plus z power minus k into BSC. You see that that is a part of this. Remember, we started with 3 unknowns, E, F and P. For E we already had an equation. Now F, we define it like this. Now notice that this term came in Aryabhata's identity. So it is nothing but phi CL into AG BG. When I substitute this expression, the first expression for F into this, that cancels an identical factor in the denominator, and we are left with z power minus k into b by p. So this is the expression for the transfer function between delta and y, and we want t to be well behaved, and that will happen if p is well behaved. So if p is well behaved, the effect of t delta y will diminish with time. If p is well behaved, the effect of t delta y will diminish with time. How do we do that? How do we make p well behaved? A popular choice is when A is Hurwitz. Hurwitz means what? It should have its zeros inside the unit circle. When A is Hurwitz, we can choose p equals A. Remember, A is nothing but the denominator of the plant transfer function. So if the plant is open loop stable, we could choose p equals A. So let us summarize the control design sequence. First choose p equals Hurwitz. For example, it could be A, and then choose f to be phi CL into AG into BG. This is the expression that we used in our 2 DOF controller design using transient requirements for step response, and we had f minus e equals PRC, or we determine E as F minus PRC as we have here, and here is the block diagram. We have got expressions for P, F and E. So P, F and E are the unknowns here, and we have come up with a procedure to assign values to these. And then we obtain this T delta, which is well behaved. So our AWC design is complete. In the figure below, F, E and P are determined. This is our anti-windup control law. RC, SC, TC are from our standard 2 DOF controller that we have been explaining in this week. This is the Scilab file that I used to carry out simulation. This is the same file that I used in the previous video. Only thing is, now we have to choose this option, simulate saturation with AWC in place. So that is given in this page, simulate saturation with anti-windup control law in place. You have to double click this. When I do that and simulate using XCOS as we did before, we get this figure. The continuous line is what we get now, and notice that U does not crank up. Moreover, it switches at the correct instant of n equals 500. The resulting output Y is given by thin line here. Here is the thin line. It never reaches the set point of plus minus 1. There is always an offset here as well as here. It can never reach, of course, because the USAT cannot exceed 1 because of the saturation block, but Y switches at the correct instant of n equals 500. This is the best the AWC can ever achieve, switch at the correct instant, although there is going to be an offset. This is the best you can do given that there is a saturation block. This is an alternative to the other solution that we mentioned in the previous video. The standard solution is whenever it saturates, disable the integral mode. That is one option. Here we have come up with a method to implement it through a 2 DOF control law. This problem is extremely important in the industry. Is there a better solution to this? The only solution is to put a larger controller capability, get rid of this saturation block. So long as the controller has a limitation, so long as the end control element has a restriction, you can't do anything other than what we have done here. I would want you to go through this carefully. I would want you to reproduce the Scilab code and make sure that you understand every step. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.